Although I didn't find that.
I got it. Sorry.
Oh, you got it. Okay, you got it. Okay, that's good. Okay, so first, welcome everyone, especially those students, and also we have so many faculties here. And this is actually our first panel at ICON, and we give this panel to introduce our new faculties and who joined Purdue this fall, and they are already excellent researchers. And but to help them to more like merge the big Purdue family more smoothly and quickly. And here we want our new faculties, Laura, Ran, Yiheng, and Philip, to introduce themselves and also introduce their research. And then after that, we will have a discussion on their research and also how their research benefit we tackle the situation related to COVID. And so each of them will have about 20 minutes. And our first, let's welcome Professor Laura Blumenchen, and from mechanical engineer. She has done research on soft robotics. So welcome, Laura. And so I will pass the microphone to you, and then you will share your PowerPoint and also introduce yourself.
Yes. Go ahead and share my screen. Just making sure, I think you guys can see that, but just verifying. Yeah, I'm getting some thumbs up, so wonderful. Thank you for the brief introduction. As was mentioned, I'm a new professor, specifically in mechanical engineering. And I'll give a brief update or a brief introduction to myself. But what I really want to focus on is, the stuff that I've been doing, for the past so many years, which I've titled here, Robust and Adaptive Soft Robotics, which I think are two of the kind of greatest potentials for soft robotics that we should all, in this field be pursuing. To start, I'll give a little bit of background of, who am I and where did I come from? So originally, I'm from Albuquerque, New Mexico. If you've never been to New Mexico, I highly recommend going, especially in the fall. You will see these various sites of hot air balloons everywhere in Albuquerque in specific, as well as just the fantastic landscape. So, growing up in New Mexico, I love deserts, I love mountains. Unfortunately, there's not a lot of that in Indiana, but I think I will adapt. And I'm excited to kind of learn a new sort of geology and weather system. After I did my schooling in New Mexico, I went to my undergrad and my master's degree in Houston, Texas at Rice University. I did my master's degree with Marcy O'Malley, who is actually a Purdue alumni. I had a lot of fun there, and I actually got to do a little bit of a side journey to NASA, who is also located near Houston, working with NASA on research projects related to exoskeletons, which I don't talk about in this presentation here, but I'm happy to talk about if anyone is interested. From there, I moved on to complete my PhD at Stanford, which I finished up last year. I show the Golden Gate Bridge here in this picture of California. I did go to the Golden Gate Bridge at least once, but as I think most graduate students would attest, I spent a lot of my time doing research instead of exploring, maybe to my detriment. Though I did get a little chance to explore and do some interesting things, I took a little detour out to Facebook Reality Labs, working with them on some of their augmented reality and virtual reality focused projects in terms of haptics and bringing the hands into virtual reality. And then finally, where I ended up now, I am at Purdue now, and happy to be here and very excited to share with you guys what I've done in the past, as well as some of my kind of interests for the future and where I think this work can grow. So without further ado, I want to give a little taste of where I see my work fitting in terms of robotics as a field in general. So this video is unfortunately very choppy. Otherwise, you'd be able to see that these robots are in a manufacturing line and they are operating extremely smoothly. In fact, this video is about a 5-10 second loop, but if you didn't know better, you would just think that these robots were just doing this repetitive motion over and over again, because that is what they're doing. And so this is kind of the place where robotics has really had its heyday so far, is in manufacturing and in doing these very repetitive, very well-defined tasks. However, a lot of things in our world don't actually look like that. So what do these robots kind of look like in a very simple formulation of it? We can think of a robot as a manipulator of some kind. It could be a locomotive or just a robotic arm, and it does some sort of motion in space. The difficulty comes when you have unknowns in your environment. So for the case of navigation, this is often if you don't know what your environmental obstacles look like. You can run in damaging either the robot or the obstacles. And this can be addressed in a lot of ways, through sensors, through other technologies, and through control. But one of the ways that I'm interested in focusing on is soft robotics. And then another place where we have a lot of uncertainty is with perhaps one of the biggest forces of uncertainty that robotics deals with, which is humans. Humans are hugely uncertain creatures and come in a wide range of sizes and kind of morphologies. And so it's actually rather difficult right now for humans and robots to interact in a safe and an effective way. So what I am interested in doing is creating systems that more effectively and robustly interact with the real world, whether that's with the static world of obstacles or with the more dynamic world of humans. For this first part of the talk, I will highlight mostly the projects I worked on in this kind of first space of navigation. But I will have a brief detour into the human interaction space at the end. So just to give, I'm not the only person working in this field, so I want to give a quick sense of the scope of this field for those who might be newer to it. So a lot of soft robotics that kind of look at interacting robustly and adaptively with the world take their inspiration from nature. So you can see little four-legged crawlers that can change their walking patterns depending on what they're interacting with. Robots directly inspired by the morphologies of animals, like this fish robot or this elephant trunk robot. And also robots that are inspired by the morphologies of the locomotion of various animals. So this is a peristaltic gait robot, which is not terribly fast, but is an interesting demonstration of what we can produce in soft robotics. And these kind of tendril, like concentric tube robots. So these, for the most part, take their inspiration from animals. What I've been working on looks at a kind of different sort of source of inspiration, which is plants. So this might not look exactly like a plant, but you can kind of understand that what's going on here, if the video isn't too choppy, is growth. So what I've looked at a lot is how can we bring in a different form of inspiration through the imitation of tip-like growth in soft robots. And so this is a very early video of what we were doing. This is just a tube extending under pressure, pulling more material from the inside. What it looks like more recently is something like this, where you have actually a human operator able to control this robot. It's much faster than a plant might grow, but it is actually using a lot of similar architecture to how plants grow and how plants move around in their environment. You can kind of think of like a creeping vine. So a lot of, because this is such a new form of movement, what I want to talk about here is how I kind of look at addressing this this new form of movement and what I've done in the past to take it in various directions and understand what's going on here. So one of the earliest things that I looked at was what does it mean to move by growing, and what can we learn and what can we intuit are important features of the growth just from that. So just thinking about the growing that I've already shown, there's some important features, specifically that there is no sliding relative to the environment, which means you have this easy movement through constrained environments. And you are also building a structure along the path. So that structure means that you can support yourself. You can also use that structure to deploy things as you've gotten to some sort of target in space. So I don't have a ton of time today, and I can share lots of other resources if people are interested in this robot in general, but I'll go through a few things that I think are the most interesting from this kind of branch of research that I've worked on. So one of those is looking at what does it actually mean to move easily through constrained environments. So I think that these videos look pretty smooth, but they're actually doing amazing things, which is I don't know if you've ever stuck yourself to this like sticky fly paper traps or sticky rat traps, but they are incredibly sticky. You can't peel yourself off of these, but the robot is able to very easily move through because there is no relative movement to the trap. And similarly, you can see it even more effectively here, where as it's going through this glue, it's almost like tunneling through the glue. But as soon as it leaves, it's done. It doesn't bring that environment with it. So you can think about this is very important if you are moving into some environment where you don't want to disturb it, or you don't want to do any sort of mixing of relative layers of the environment. You're not really tracking in dirt from one area to the other, which can be potentially interesting. And just to put a little math in, because even though it is very early in the morning, I don't want to get away with not looking at some math. We can do some experience to look at what exactly, how can we classify this this movement through constrained environments by just looking at what is the pressure to grow through different surface environments, adhesive, rubber, Teflon, so a range of both adhesion properties as well as surface properties for friction, versus how hard is it to pull the same structure through if we were talking about traditional locomotion of actually having to move your body relative to an environment. So just comparing this, plotting out the data for this bottom one, pulling through first. As expected, we can see that a low friction environment results in a relatively low force that does grow as we displace further into this gap. Whereas a higher friction environment means obviously we're going to need a larger force to move. And the tape leads to these stick-slip events as we're kind of separating from the tape, but it is also a incredibly large force relative to the structure, nearly pulling the structure apart. If we look instead at the growing, we have some decent amount of force. It's larger than actually what it takes to grow through Teflon, or to pull through Teflon, but it doesn't depend on displacement. And it also doesn't depend on surface properties, as we can see that the same force, same internal pressure is required for rubber as well as tape. So what we can see here is that essentially the function of this robot can be described pretty easily, since it is almost entirely separated from its environment just by a constant offset force based off of the properties of the robot itself. If we turn our attention to a different property of growth, looking at building usable structures, we can show a few different, really, I think, convincing demonstrations in terms of that. So this video might be coming through a little choppy, but the basic idea here is if you aren't able to access an environment for some reason, but you need to get a leverage in there to do something like turn off a valve, a growing structure like this allows you to build a physical structure that you can use to apply forces. Here, using the structure internally, pulling on the structure in order to pull on this hook at the end and close the valve. Similarly, like I mentioned, you can use the structure in order to deliver things. And so here we are growing through a gap with water. And so when we get to this fire at the end, we melt a hole in our tube and put out the fire with a little bit of water. So these are, I think, cute demonstrations. They're kind of all pre-planned, but this is an area that I am more interested in pursuing here, is looking at what can we do with this structure building capability, especially in terms of construction, in terms of building usable pathways in our environments. So one thing that I've already started doing in that area is using soft growing robots to match target shapes. So for example, this knot here, we wanted to grow the robot into a knot. Some of my past work looked at how do we actually design a tendon. So this essentially, to quickly explain this, is the shape of an actuator on the robot body, how it kind of curls around the length of the robot versus its circumference, and where you have to strain the material. And if you follow this plan, you can in fact get the robot to take on the knotted shape that you're interested in, and it is, you know, measuring it the knotted shape that we expect. But this, I think, also shows, is a great demonstration to show why it is actually important that this is a growing robot. So these videos are a little slow, so I'll just kind of skip ahead to the end here on this one. But you can see on this bottom one, hopefully, that if you are already a fully grown structure, you have to sweep out this huge area in order to try to form this knot structure, and you can't actually do it because of self-collision. But if you form the structure while growing, you're able to stay in a relatively confined area, as well as keep that knotted structure even if you release the actuation. So this is an interesting area both of modeling, of design, and of control, for understanding how can we control these structures, give some amount of control to a human who might want to design something on the fly, as well as how do we leverage this ability to grow while actuating. And then the last thing I want to talk about, which is a little bit tangential in this realm of the growing robots, but I think it's very interesting for the area of control, is this project that I worked on of robust navigation through leveraging environmental contacts. So this looked at how do we understand environmental contacts in order to predict where a robot might go. Here there is no steering involved, and it just kind of freely goes where it wants to. And so the kind of obvious conclusion to this work is, well, we should use this to design robust planning. And that's what we looked at. So given a desired target path, if we take a model like this that tells us how we bump into obstacles, we can actually design a shape of a robot that intentionally contacts obstacles with this knowledge and reduces our uncertainty at getting to a target location, versus just, you know, your typical kind of path planning algorithm of making this shape exactly. So I think this is also a really interesting area, not just for growing robots, but for potentially path planning and navigation in general for soft robots. How do we leverage more certain pieces of our environment in order to reduce our uncertainty that is often found in soft robot navigation because of the compliance. Okay, so that was a very quick kind of speed through a lot of the interesting features of the navigation work. I've got a few minutes left, so I'm going to talk quickly about the human side of this. Just quickly going through why would we want to interact with humans? So we might want to provide haptics for driving, so you don't have to look at your phone, for interacting with virtual objects, or for assisting people who might not be able to fully do tasks themselves. So we've done this with the growing robot. Excuse me. Looking at wrapping around the arm in order to provide haptic stimuli. This might be a little bit of a creepy video, but it does kind of show what a deployable structure could possibly do. And also looking at using additive manufacturing to create easy to design compact actuation that can be used for wearable systems. So the interesting thing here, I don't have a lot of time to describe this, but it's actually relatively easy to build these models of their force output just from knowing one model, both in terms of scaling up and in terms of the number of actuators that you're using. And I think with that, I've probably overdone my time a little bit, but I want to leave some time for questions. So I'll just leave on this cool video of how we actually use those actuators for this starfish robot. Okay. And if anyone has any questions at this time, I will be happy to take them.
I guess everyone's watching the video.
Yeah, you will see two of the features of soft robotics that I think are important to discuss, and maybe we'll get to this, but this is 20x. So that is, soft robots are often slow. So it's important to talk about that in regards to how they're useful. And you see this whole bunch of cords going off to the side, which is one of the dirty secrets of soft robotics, is where do you actually get your power from? Yeah.
I had a quick question about the robot robots. Do you, is there a need for sensing along the entire length of the robot, or what's the biological analogy there? Is there...
Yeah, I don't know if there's so much a need. It's a potential interesting area to explore, though. So you can imagine that these systems could be deployed for long term, and we've done ones that are like the length of a football field. So if you wanted to deploy one, for a week or so in some area and sense an entire area, that could be possible if you have sensors along the entire length. As far as control, it actually seems to be that as long as you have sensing at the tip, you are able to get pretty good control of the system. Yeah. Depending on how you build it. Yeah.
Okay, any other questions? Peter, okay, if not, we'll move to we will first thank Laura. It's a very interesting topic and presentation. And so next we will welcome Ran Dai from AAE, and Ran's research more like in drones and control and dynamics. So Ran, so you could share your screen and introduce yourself.
Good morning, everyone. My name is Ran Dai. I joined Purdue University School of Aeronautics and Astronautics as an associate professor. Before that, I was an assistant professor at Ohio State University. I got my bachelor degree from Beihang University in China. And after that, I started my journey at the United States. So I got both my master's degree and PhD degree in aerospace engineering from Auburn University. After that, my first job is at industry. So I worked as a research engineer in dynamics research to investigate the traffic reconstruction and prevention technologies. After 2 years in industry, I feel I still miss the freedom of academia. So I went to University of Washington as a research, as a postdoc. So there I was involved in a Boeing-funded project to develop distributed control algorithms for the Boeing 787 electrical system. So that's most about my experience. So today, I really appreciate this opportunity to introduce myself and my research work. So in the following, I will present some ongoing projects and previous projects conducted in my group. My research focuses on developing advanced control and optimization methodologies to improve efficiency and sustainability of a wide range of autonomous systems in challenging missions, such as the aerial vehicles in communication networks and target tracking, the Mars rover in planet exploration mission, and landing vehicles in planetary travel. So our goal is to realize the high-level autonomy of these systems in complex missions involving challenging constraints or nautical decisions. So to overcome technical challenges, especially the heavy computational load to generate autonomous control commands, we developed motion planning and decision-making strategies based on integrated modeling, optimization, and learning methods to enable high-level autonomy. For this talk, I will present our research work in this area. So one problem we are investigating is the optimal guidance of spacecraft entering power descent and landing mission. Both NASA and SpaceX, they are investigating the human Mars mission. As we know, Amazon does not deliver to Mars. So the human Mars entering power descent and landing mission requires to deliver a high payload, such as the astronauts and their supplies from the entering interface at hypersonic speed to a predefined landing station on the Mars surface with a high precision. So basically, we want to deliver the high payload within a specified range that is smaller than 100 meters. So the high precision landing at a developed station at Mars is very important. As I believe most of you here probably watched the movie Martian. So unlike the astronauts in the movie Martian, we do not expect our astronauts to walk several days or months to the already developed station. So during the entering, power descent, and the landing mission, the fuel is limited, and the entire mission is composed of two phases, the entering phase and the powered descent phase. In the entering phase, we will use aerodynamic forces to decelerate the vehicle. As we know, the Mars atmosphere still has very thin air, so we want to use that atmospheric forces to decelerate the vehicle. And following that is the powered descent phase. That will require to generate thrust from the rockets to decelerate the vehicle. So as we can see, the two phases have different dynamics and constraints. So what we want to do is we proposed an end-to-end guidance different from existing guidance that controls the two phases separately. We want to make an integrate mission planning that will make decisions on the two-phase trajectories as well as the transition point together to improve the fuel efficiency. So here is one of the simulation results of the end-to-end EDL guidance. As you can see, the first phase here is the entrance phase. It will last about several minutes. And following the entrance phase, at the end, the very small duration here is the power descent. So the red one represents the thrust. So since the power descent phase is relatively shorter, I provided different views on the left side. So to verify the feasibility of generating real-time fuel efficient maneuvers in dynamic environments, we are building a landing vehicle using 4 propellers to mimic the motion of hypersonic inflatable aerodynamic decelerator. That's the famous Hyatt decelerator. So the left one is the picture I took last year when I visited the NASA landing. So they are building a landing vehicle with diameter about 10 meters. So the right side is our design. So this is still ongoing work. Another problem we are investigating is the UAV path planning with task allocation, where a UAV is required to visit several waypoints using minimum fuel or minimum time. The decisions, including continuous variables, represent the planned path, and the discrete decisions representing visiting sequences. So when we have both continuous and discrete decisions involved in an optimization problem, it increases the computational load by the exponential order. So using our unified optimization algorithm, here is the one we can solve the integrated path planning and task allocation problem in real time. So here is one simulation result. And when the vehicle is following the planned path, we change the avoidance zone, and our algorithm can quickly regenerate a new planned path that avoid this new avoidance zone. So another type of autonomous systems we are working on is solar-powered area and ground robots. These robots are capable of harvesting energy from the environment and charging the onboard batteries as a backup to extend the endurance time or realize persistent operation in ideal scenarios. The object for this project is to develop a next generation solar-powered robotic systems that integrate heterogeneous area and ground robots to achieve long duration. So we call it long-term autonomy. So one application of this type of robots is in the outdoor sustainable mission. If we want a robot to consistently visiting several important targets, so we want to use the environment energy to supply the power instead of recalling the vehicle to charge them. So here, ground robot is required to persistently visit several assigned waypoints. In this example, we assign 4 waypoints. each trip need to be finished within a specified time. And as you can see, for these robots, we have 18 watts solar panel mounted on top of that. And we try to use this solar power harvesting equipment to supply the power to realize the persistent operation. So the robot has developed the energy awareness capability by constructing the solar irradiance map from image processing. So the map you see on the left bottom color is a solar irradiance map from our image processing method. And before the robot enters the area, we will use the Google map to construct a draft solar irradiance map. And after the robot enters the area and persistently visits the assigned waypoints, they will take images along the trip to reconstruct the map to improve the solar irradiance precision. As you can see, comparing the two images we have here, when the robot enters the area using the images in the real time, they can have better configuration of those shadowed area underneath the tree. So the second trip, the robot has less energy loss compared to the first trip. So considering some challenging operating environment in both Mars and the Earth, with different types of obstacles, some objective points may be located at an area not easily accessed by those rovers. So we developed a cooperative robotic team composed of a charging station and jumping rovers that can jump and roll to overcome environmental obstacles in exploration missions. The jumping capabilities, as you can see, this is the jumping rover we constructed. These jumping capabilities provide a flexible form, or we will say a flexible locomotion mode. They can leap and land on top of obstacles instead of navigate around them. And these jumping rovers on the left side photo, you can see they can dock at a solar-powered charging station wherever they need extra power. So here is the scenario of deploying the jumping rovers for the multi-waypoint visiting mission with obstacles. So all those boxes will show their obstacles. And some of the objective points, like objective point 4, are even more critical. And the two rovers can deploy using our mission planning algorithm. On the point of the mission, they will get stopped at the charging station to get extra power. So to extend the operational time of quadcopters, we also designed and constructed a large-scale solar-powered quadcopter. As we know, a traditional quadcopter, like the DJI, they can barely achieve about half-hour flight duration. So we use those existing quadcopters in agriculture applications, for example, to scan a standard size farm in Middle West. When the vehicle consumes all its power, it can only cover about 10% of the standard size farm. So we have to recall those quadcopters to recharge them and deploy them. So considering those limitations, we designed and constructed a solar-powered quadcopter. We have 88 pieces of solar panels mounted on top of them. Those solar panels can supply around 100 to 200 watts power in sunny days. And the motor-to-motor distance here is about 6 feet. The overall payload is about 10 pounds. So we deployed our solar-powered quadcopter in a sunny day last year, the 2 years before. So here is the flight test. The quadcopter can maintain the hovering status for about 18 minutes. However, without the solar panel, it can last around a half hour. So you can see the plot here represents the harvesting energy and the energy consumption. So at the end, I would like to acknowledge the hard work from my former and existing graduate students. We cannot achieve those work without their hard efforts and the funding agencies. So that's all I have. Thank you. Any questions?
I had a quick question, Ron. So the solar powered drone, what is the additional capabilities in terms of payload past the solar panels, or is most of the drone only able to just carry the solar panels that they have?
Oh, they can do most of the things like existing quadcopters, like take videos, do the surveillance and yeah, some monitoring work, but it will have extended operation. So yeah, that's like a standard drones they can do.
Very cool.
Okay, thank you, Ran. So, for our audience, if you have any questions, you could feel free to unmute yourself or type in the chat window. And so we will move to next. Will be Yiheng Feng from a civil engineer, and his research expertise is in autonomous and connected vehicles. So we'll pass the microphone to Yiheng.
Thank you, Shaoshai. Can you see my screen?
Yes.
Okay, great. Okay, yeah, thanks for the invitation, and I'm very glad to be here to present in this ICON seminar and to introduce my research. So what I'm going to talk about today is the connected and autonomous vehicles with smart infrastructure. And first, I'm gonna introduce a little bit about myself. I was born and raised in a beautiful city in China called Hangzhou, and I got my bachelor degree from Zhejiang University in China, and my master degree from University of Minnesota and PhD from University of Arizona. And after that, I joined University of Michigan as a postdoc first, and then a research scientist. And I moved to Purdue about 1 month ago, and it's very exciting to have this new job. And so on the left-hand side is some of my personal information, including hobbies and some social media information. So today, of course, I'm going to mainly talk about my research. So this slide shows actually where my research fits in the entire transportation system. So if we look at the entire transportation system, we have three main components: travelers, vehicles, and infrastructure. And we are saying that we're entering this new era of smart transportation. So although the three components remain the same, but their features and their behaviors actually changes a lot. My main research area is actually focused on the interactions between the smart infrastructure and the smart vehicles. So then what other interactions? I summarized the three, or this is the three directions that I'm really interested in. So the first one is how to leverage the new data source and control capabilities from CAVs to improve existing infrastructure operations. So first, because of the connectivity, now the transportation infrastructure can receive proactively broadcast the information from those connected vehicles. That is significantly different from our current data collection method, which are from the infrastructure-based sensors. With the new connected vehicle data which provide much more information, the infrastructure system should have the ability to make better decisions, control decisions in terms of improving safety and mobility. And the second point is that because now with the vehicle autonomy, so the vehicles can also be controlled, which extends the control framework from the previously only the temporal, we can only control traffic signals, to spatial temporal. Now we can also control the vehicle trajectories on the road. So the integrated control framework may further improve the system performance. So this is one direction. And the second direction is on the other side of the problem is how to improve the current infrastructure to accommodate new features of the CAVs, which means what new capabilities of the infrastructure should have to support the operation and deployment of the CAVs. So first, I call it infrastructure adaptation, means whether, for example, whether we need new sensors, whether we need new communication system, or even whether we need to redesign the infrastructure to accommodate the CAVs. And the second is the cybersecurity of the transportation infrastructure, which is a new problem because now the infrastructure is connected to the outside world. So it may bring some potential for cyber attacks. And finally, the third direction is how to use infrastructure to facilitate the CAV testing and the evaluation, because this is a very important pre-step before the CAVs can be really deployed on the road. So I will give a few examples of my current and previous research on these topics, but due to the time limit, I mainly try to introduce the problem and introduce what we do on a higher level. So the first example is about the cooperative driving. That is how to integrate the infrastructure and the connected and automated vehicles together to provide an integrated control framework. So basically, we developed this hierarchical framework, which has 3 levels. On the vehicle level, so each CAVs plan their own trajectories, giving the high-level guidance from the infrastructure side. So here we consider a mixed traffic condition with 3 different type of vehicles: CAV, and the regular vehicle. So the differences are CAVs are both controllable and observable. CAVs are only observable but not controllable, where the RV is not controllable and not observable. So for CAVs, they can plan different driving behaviors, like they can form the CACC platooning, they can plan an eco-vehicle trajectory to save fuel consumption and emissions, and also they need to make sure the collision avoidance with regular vehicles. So then on the intersection level, so the intersection is responsible for optimizing the traffic signal parameters as well as giving high-level guidance to the CAVs. For example, which lane you should take and what time of arrival, what time you should be arrive at the intersection, to better coordinate and guide the trajectory planning in the vehicle level. And then we have the corridor level, which try to promote the coordination between different intersections and to promote the progression. That means the platoon, if we want the platoon to pass consecutive intersections without stop. So how to coordinate the traffic signal parameters on the entire corridor. This is the task of the corridor level. So we apply different methodologies for this control framework. For example, traffic flow theory to model the vehicle behaviors and to estimate the traffic states. We use the optimal control to plan the CAV trajectories, and we model the entire integrated control framework to our mathematical programming problem. So the next application talk about is about the infrastructure adaptation. That is kind of the in the far future where all vehicles are connected and autonomous vehicles. So in this case, we build an integrated path planning model for all the CAVs on the road on the corridor level. So basically, we plan the CAV trajectories along the corridor. And in this case, we remove the physical traffic signals at intersections, and we just model the collision avoidance at the intersection area for the CAVs to avoid collision. And also, we actually relax this lane assignment. So if you look at the current road, each lane has its own direction, right? The through lane, left turn lane, or right turn lane. So in this case, the lane assignment is flexible, which means all lanes so vehicles on each lane can go for each direction. So in that case, we can, in a great extent, to minimize the lane changing behaviors on the road. And it is shown that actually the lane changes are actually very disruptive to the traffic flow. So in this case, we can greatly improve or increase the capacity of the road and reduce the total delay of the entire system. So the next application is on the other side of the problem is we want to look at the cybersecurity problem of the infrastructure. As I mentioned, because now the infrastructure becomes connected to the outside world, are receiving information from the outside world. That actually opens the door for cyber attacks. Actually, there was a attack example in the New York City. So a security expert hacked into the wireless vehicle detection system so that he can manipulate the input data to the traffic control system. So that can cause huge consequences, negative consequences to the intersection operations. So to study this cybersecurity problem, the first step we do is to analyze the vulnerabilities of this we call connected infrastructure. So we identify two types of attacks, directly attack and indirect attack. Directly attack means if the attacker can physically access the controller, then he or she can manipulate freely the signal timing plan. This can cause the most significant damage to the system, but it's very difficult to physically access the hardware because most of the hardware are protected in the signal cabinet and also protected behind the firewalls. So the next is indirect attack, means if the attacker can compromise the connected vehicles or can compromise the vehicles on the road, and then the vehicles send the falsified information to the traffic control system to influence the traffic control decisions. This we think it is a more a realistic attack because the vehicle owner can be malicious and he or she have arbitrary access to their vehicles. And a lot of previous research shows that it is possible to hack into a more modern vehicle and send falsified information. So we use this as attack model, and then we build optimization models to generate the falsified vehicle trajectories that can generate suboptimal signal timing plan. So we actually found this kind of attack is very significant we only need one single vehicle to cause, to make the intersection from the under-saturated traffic condition to over-saturated traffic condition, like in this case. And if the attacker can last longer, then there will be cascading factors, because those queue spillovers will be extended to upstream or downstream intersections to further influence the entire traffic network. So, the reason we want to study these attacks is because we want to find the vulnerabilities and to guide us, to provide us some insight to better to design our defense system, right? We don't want to be the bad guys. So one observation we got from the attacks is that in order to launch effective attacks, those falsified vehicle trajectories should be abnormal. Like in this case, this red curve is the falsified trajectory. And you can see actually, if this is a time-space diagram, you can see it slows down when the leading vehicle is still far away. So this is kind of abnormal behavior. So that inspired us to model this falsified trajectory detection problem or identification problem by abnormal detection. So we borrow, we are also inspired some methodologies from the natural language processing community. It's called word embedding model, because if we think the sentences and the vehicle trajectories are actually very similar. So we developed this trajectory embedding model, and we train a neural network to find the vector representations of each trajectory point. And we use the vector distance as a distance matrix to present the distances between different trajectory pairs. So the main idea is that if the trajectories are normal, their distances should be short, and the distance between the abnormal trajectory and the normal trajectory should be large. So then we apply a clustering method to identify abnormal trajectories versus the normal trajectories. And when we apply the methodology, the detection method to our previous attack case, and we find that our detection rate is more than 99%, which is very high. We can identify almost all the attacks. Okay, then finally, the third direction is about the CAV testing and the evaluation, how we use the infrastructure to help this. So first, this is a very important question, because CAVs need to be tested before they can be really deployed. So we can, of course, we can test the CAVs directly on the road, but actually that's not safe, right? So the left figure shows the Uber accident in Arizona 2 years ago, when Uber was testing their autonomous vehicles. So it will bring very huge public risks. So instead, we can test the vehicles, the CAVs, in the closed test facility first, before we deploy them on the road. So the right figure shows the test facility at University of Michigan. So the test facility has some advantages. For example, because if it's closed, so we don't have public safety issues. And also we use the real vehicle to test, so it's actually more realistic than the simulation. However, there are also two major limitations of the closed test facility. One is because of the closed, so there's no background traffic, but most of the testing scenarios require the interaction from other vehicles, from other traffic to interact with the testing vehicle. And second, because it's closed, there's no testing scenario. So we want to solve these two problems. So to solve the first problem, we developed this augmented reality testing environment. So the key concept is to generate virtual background vehicles from the infrastructure side and to synchronize with the testing vehicle in the real world. So this video shows in the demo we implemented in MCity. So the left-hand side, this is the simulation world. So the blue vehicles are all the virtual vehicles generated from the simulation. And the yellow vehicle is the representation of the real vehicle in the real world, in the simulation world. Right, so the right-hand side shows it's in the real world. You can see the vehicle. It's a level 4 CAV So it drives by itself. So in the real world, there's no real vehicles on the road, but what the vehicle sees, you can see all the rectangles here are the virtual vehicles from the simulation. So that although the vehicle is driving on empty road, but it sees all the virtual vehicles and can interact with each other. So in this particular case, like we generated a red light running virtual vehicle, so that so the real vehicle detects a potential collision and stops at the stop bar to avoid the collision. So one of the two, there are two very significant benefits for this system is that one, because we can manipulate all the virtual vehicles, so we can design any scenario that we want, right? Like the previous red light running vehicle case, it's a rare case in the real world. And so if in the real world, if the CAV runs for like even 1,000 intersections, it may not run into a red light running vehicle. So in this case, we can greatly increase the intersection capacity, so the testing efficiency. And the second is because it's the real vehicles interacting with virtual vehicles. In this case, it's a virtual train, right? So that even an accident happens, there will be no real damage. So these are the two major advantages that we are developing this system. And in this system, you can see all the vehicles are synchronized, their behaviors are synchronized in real time. Okay, so this platform actually only provides, this testing environment only provides a platform for designing different scenarios. But a more important question is, how do we design these testing scenarios in a more systematic way? So the difficulty here is that the testing scenario, the number of testing scenarios is almost infinity in the real world because of the complex Netflix driving environment and complex human driving behaviors. So then the research question would be how to identify a set of critical scenarios, which is only a small portion in the total scenario space, which can accurately and more efficiently evaluate the performance of the vehicles. So we propose this new criticality definition. It's a combination of the maneuver challenge and exposure frequency. So the intuitive is very straightforward. So we want the scenario to be as challenging as possible first, and we want also the scenario to be as frequent as possible, that's as more common in the real world as possible. So the combination of this is the criticality. So we apply different methodologies to find the critical scenarios based on the dimensions of the cases, using mathematical programming or the reinforcement learning, or even deep reinforcement learning when the dimensions are really high. And we also use the importance damping theory to prove that our method is accurate, which means our performance measurement is unbiased and more efficient. That means our tests have smaller variance so that we can use much fewer number of tests to achieve the same accuracy level. I think that's all I have, and I'm happy to answer any questions.
Okay, thank you, Yihan. Thank you. Since we are behind the schedule, so we'll save the questions after Philip's presentation.
Yeah,
so
sure.
Philip is from ECE and graduated from UIUC. Actually started to know him since he was a PhD student. Okay, Philip, your turn.
Thanks, Joshua, and thank you to you and Shreyas for organizing this event and for inviting us to participate, and also for creating ICON. It's exciting. I'm excited to be here. And just for time, should I try and be shorter than we said, or?
Oh, take your time. You know, each one about 20 minutes, so we still have time. Okay,
great. So yeah, my main research focus is on epidemic spread over networks, and looking at modeling, estimating, and controlling these systems. So just background, I grew up in Cambridge, Massachusetts. This is actually a picture of my eco project, part of my eco project that I did to clean up part of the neighborhood near my house. I then went to Brigham Young University in Utah, where I did my my undergrad in math with minors in music and computer science, and then I did a master's degree in computer science. Both these degrees, my honors thesis and my master's thesis, I did under the supervision of Professor Sean Warnick, who did his PhD at MIT with Lunsor Dali. And then I went to Illinois and did my PhD in the Coordinated Science Lab with Carolyn Beck and Angelia Nedich. I also worked a lot with Professor Bashar there. And then I was fortunate enough after that to run away for a year and a half and take a break from the US and live in Sweden, where my kids turned into full-fledged Swedes. They've kind of recovered from that in the last couple of months, but we all loved it and missed Stockholm. And there I was able to work under the supervision of Kalle Johansson and also work with Henrik Sandberg a bit. And it was a great experience, but we're really excited to be here and be part of the ECE department and joining ICON as well. So just kind of motivation, I don't think we need to do much of this, but yeah, studying epidemic spread over networks has been the focus of my research for the last while. Plenty of motivation. This was in May, and obviously the numbers are even worse now. I need to get an updated slide in here and haven't had time. But yeah, so kind of going back a little bit further, we look at what was the birth of epidemiology, or the field of epidemiology, which was Dr. John Snow. He was a physician in the 1850s, not a character in Game of Thrones. He drew this map to illustrate the number of deaths per household, cholera-related deaths. So people were dying from cholera, not just in London, but all over the world, mainly in big cities. And he drew this map to show the city officials that all these deaths were centralized around this pump, to convince them that this water pump was the source of the outbreak, and it wasn't spreading through the air as they thought at the time. So he convinced them to remove the water pump, and people stopped dying. So developing mathematical models of epidemics is not a new thing. Bernoulli actually did proposed the first model in the 1700s. But as the world has changed and we've become more connected and more networked, this necessitates new models. So we're going to look at some models. Namely, the main focus will be SIS models, but then at the end we'll talk about some different models with more compartments. So a simple SIS model assumes that everyone is either susceptible or infected, and you transition from being healthy or susceptible to becoming infected at some infection rate beta, and then you heal at some rate delta. And the dynamics look like this. Your rate of change of your susceptibility has a negative effect on how you transition to becoming infected, and then you heal at the rate delta. So you get an additive term here, and then the opposite happens for becoming infected. And if we assume that, we can see this nonlinearity here, so it makes the dynamics a little bit more complicated. And further, we can see the nonlinearity even better if we assume a fixed population size, so we can replace S with N minus I, and you see the quadratic term in the infected state. I removed for interest of time, I removed my networked motivation slide, because this model assumes that the underlying graph is completely connected, that everyone mixes instantaneously and equally, which we hopefully in ICON know that that's not the case in most cases, most applications. So then we can scale the infection rate by this term here, where A is our graph structure, and so it shows the connections from J to I, And X is our state, or how sick the jth neighbor is. So, and then the healing rate is the same, you just have a delta. So for each agent I, your probability of being infected, or if each node is a subpopulation, maybe it's thought of as a proportion of the subpopulation that is infected, heals at a rate delta and becomes infected, scaled by how healthy they are, 1 minus how sick they are, multiplied by beta, their infection rate, and how sick and how strongly connected to those sick neighbors the IF agent is. And so this is a model that's been studied for a while, but we've done work to extend it in a number of areas, looking at time-varying networks, looking at competing viruses. So if you have more than one virus spreading in a population, how can you, and they interact in the sense that only one person can be infected. We've also looked at including human awareness. So if you're aware that a virus is spreading and you change your behavior, how does that spread? How does that affect the spread? And we've also coupled these dynamics with opinion dynamics as well, among a couple other extensions. But the one that I'm going to talk about today is looking at real data and how we could use real data to capture this behavior, namely in the context of the snow data that I started with. So discrete, and for this we look at discrete time model, because the data that you get is either in like a daily form, because COVID is such a big deal, we're getting daily numbers usually. Similarly, John Snow, in addition to adding up the total number of deaths, he also did the number of deaths per day. So we had daily data here, and for other viruses, they sometimes aggregate by what they call epidemiological weeks. So you get, for each week, you get one data point. So discretizing the model that we looked at before, instead, now we're looking at discrete time K, H is our sampling parameter, and the rate of change is just what we had before as a derivative. So we're applying Euler's method here. And then we can rewrite this model in matrix form, where B is a diagonal matrix with the infection rates. Similarly, D is a diagonal matrix with the healing rates, and X is a diagonal matrix with the state. So you still have this nonlinearity here. The X is multiplying the X, and then A is just our adjacency matrix. And these three matrices are important. So it's the infection rates, the connections between the agents, and the healing rates. We're going to use that moving forward. So the first result we're going to look at is a generalization of the reproduction number. I think since this has become kind of a term that's used often in the media, you kind of understand what it is, but it's a number on average of people that become infected from one infectious person over their whole period. So if it's less than or equal to 1, we're going to be okay. So we generalize that to include the graph structure, where rho is the spectral radius of this linearized system. And if it's less than or equal to 1, then the healthy state, or where no one is infected, becomes asymptotically stable. And it's in this domain of attraction where the model makes sense between 0 and 1, i.e. it's global in the sensible domain. And how we can see explicitly that it's that it is a generalization of the reproduction number if we look at the fully connected graph with homogeneous spread. That means everyone reacts to the virus the same, every node. And when we do that, the reproduction number is beta over delta. And if this is less than or equal to 1, it's equivalent to the spectral radius of the expression in our theorem being less than or equal to 1. That is, for the connected graph case, this is the same condition. But this holds for any graph structure. We need irreducibility for the equality, but less than 1, we actually have exponential stability, and you don't need the underlying graph to be strongly connected. The complement, or excuse me, the converse of this condition is the spectral radius of this expression being greater than 1. We've proven that there are then two equilibria: the healthy state, where no one's sick, and some endemic state where everyone is at least possibly a little sick. And further, if we have an endemic state, if it exists, then we can write this expression. The ratio of the spread parameters is equal to this function, where of the endemic state and the graph structure. And we're going to use this to apply, to learn the spread parameters, or the ratio of the spread parameters, from the John Snow data. And for the John Snow data, we're going to use the state is going to be the cumulative number of cholera-related deaths up to that point. And the endemic state is going to be our map right here. So our X star is going to be, we're going to pull from the map. So the number of deaths per household, and each node will be a household. And so we assume that the water pump is also a node in our network, and it's and then there are other pumps in the area that are healthy. So the pumps are these diamonds, and the households are represented by these nodes, by these circles. And so the circles are scaled by the number of deaths that they had, and so each circle corresponds to a household in the map. And he also, as we saw at the beginning of this section, recorded the number of deaths per day, cholera-related deaths per day in the relevant time window. So what we're going to do is we're going to pick a graph structure, namely the star graph, because we know that cholera spread through the pump, and that's our last node. And then it can also spread through bodily fluids. So households sharing a bathroom can affect each other. And this 1/10 that's hidden right here is its workhouse, because there were only a couple of deaths, 4 or 5 deaths from the workhouse, but there were over 400 people that lived there. But they had their own water pump and apparently drank a lot of beer. So they didn't walk down here to get water. So this is what our graph structure looks like in our initial condition, with the water pump being contaminated and every household being healthy or not having any deaths yet. And what we did is we used the previous corollary to recover the ratio of the spread parameters, set beta I equal to 1 for every agent, and then simulated using this initial condition and this graph structure. And when we did that, we added up the total number of deaths per day from our simulation, and we got this red curve, capturing the behavior surprisingly well. And because this is the real data, the blue line. And while this isn't exactly probably how the outbreak occurred, it's not, we don't know exactly how it occurred, right? So the number, this is what it looked like on the node to node basis, because that was the aggregate behavior. And while we don't know if it captured it perfectly, it did capture it to some degree. So the takeaway is that these models that we have can be used to design some control algorithms. So now we'll talk briefly, given the time constraints, about potential mitigation strategies. So this is the continuous time model again. So we have a couple knobs. The first knob is the graph structure. So if you know somebody's sick, you can just cut them off. Or if you want to save, if you know there's something spreading in one dorm, maybe you cut them off and don't let them interact with the other dorm. Similarly, we can also, or alternatively, we can affect the infection. We can affect the infection rate. So we can choose a subset of nodes to change their infection rate and how they become infected from their neighbors, which effectively just reduces the incoming edges. And then what else we could do is we could also affect the healing rate. We could boost healing rate through some sort of antidote administration. And we have a number of works in addition to these listed below where we do these different techniques. So briefly, just to finish, I just want to talk about how we've extended these, working on extending these models, this type of work into different models. So we've looked at SIR, networked SIR models. We're looking at SEIR models where you have an exposed state in between, or you have an asymptomatic state is another one that we've looked at, SAIR, to capture the behavior of COVID. We're also thinking about how to turn testing data into the states in these models and how we can use the data that's available to accurately estimate the underlying epidemic states. Additionally, we're also thinking about transportation and how transportation plays into the spread, and other infrastructure as well, such as water and water networks, and thinking about how we can design safe infrastructure that's resilient to possible outbreaks. But yeah, just briefly, we introduced one extension looking at the SIR model where we treat the water as a different type of node. So we introduced, this was to capture the snow data better. So instead of treating the pump just as a normal node in our graph, we treat it as a separate entity. So then you have the water contaminate with just the people infecting it and it having some decay rate on it. And then in addition to becoming infected from your neighbors, you can also become infected from the water source. And we've also allowed for, we also look at infected states and then removed, which means deceased here. So we were able to fit the data as well, and we looked at a homogeneous because there's more parameters here, and less data. There's not that much data, so you can't learn that many parameters. So we had to kind of make some assumptions on this, and we were able to capture the behavior with a more specific model, but less parameters in a fairly good way as well. So this is the number of deaths. And then just to finish, I want to say thank you so much for listening, and I'd be happy to take any questions.
Thank you, Philip. And so any questions to Philip and also Yihan? We actually, after the 4 presentations, we are into the more like a mode for free discussions about any research or related, or this this 4 new or any advice to the 4 new faculties from already our senior faculties, or the faculty to some advice to students.
Oh, I meant to add a plug for my class. I'm teaching a 595. Well, actually, I'm proposing it in an hour in the graduate committee, but I'm hoping it'll be approved because I'm already building it for teaching a class called Epidemic Processes over Networks next semester. It'll be ECE 595, and if there are any students that are interested, I'd encourage you to enroll.
Oh, cool.
Hey, this is Dan Feng from Aerospace Engineering Department. I have 2 questions, one for Yihan and one for Philip. Can I ask questions now?
Yeah, do you want to ask?
Sure. Go ahead.
Yeah, I will start with Yihan. So, I don't think we have met each other before, but I got my PhD in civil engineering doing transportation. And actually, most of the graduates from my advisors group, they are professors in civil engineering, except myself. And I believe most of them are doing connected and autonomous vehicles. And I usually talk to them, I usually ask them the same question. So I fully agree with you. For a better transportation system, we have to coordinate and cooperate between 3 elements. Drivers, I wanted to say pilots. So drivers, vehicles, and infrastructure. And you did mention the smart infrastructure, right? So what is your opinion or your your comments on type of like features or requirements for the structures to be smart?
Oh, okay. I think that's a very good question. So to answer that, so I think people are more familiar with the concept of vehicle automation level, right? From 0 to 5, from no automation at all to advanced driving assistant to partial automation to fully automation. So I think the role of the infrastructure should apply a similar concept where our current infrastructure is conventional. It's not connected. It's do not provide any information. So I think along this way, we can also define different levels, or we can call maybe in intelligence levels of the infrastructure. For example, basically, the first step, infrastructure can provide some static information to the vehicles. And then the next step could be, for example, provide some dynamic information to the travelers and the vehicles. And then maybe the next step could do the cooperative sensing with the vehicles to enhance the perception capabilities of the system. And finally, probably we do the cooperative automation, or we say cooperative driving or cooperative control, also to participate into the decision-making process and to combine with the vehicle to cooperatively or integratedly to optimize the traffic flow. So that's kind of my opinion on how the infrastructure should be connected and smart.
Okay, thank you very much. That's very good. It's very inspiring. Thanks. My next question is for Philip. So, what kind of suggestion you want to bring to the CDC and the Trump administration to get this situation better as a control engineer?
What do we want to do? Is that what you're saying? What should I?
Yeah. What type of like a recommendation if you can, to make to the CDC and our administration?
Yeah, getting into politics is a little tough. I think they should have been testing from February. I think we made a big mistake by not testing. Like as soon as we knew, like as soon as the genome was released by China, we should have had tests up and running, and we should have not pretended like it wasn't going to get to us. That would have been the first thing. The second thing, I think, yeah, the balance between trying to figure out whether we should open and what to open, what not to open is really, really hard. And one of the things that in one of my proposals that we touched on that we're going to, it's just a 1 year, but we're going to kind of build off of our work with this transportation stuff, is thinking about the economic factors and trying to bring someone in, because I think that is the hard part. It's just like any control question, right? You have to factor in safety, but performance, right? So the trade-off between like economics and not are a very difficult question. And I think Purdue and University of Illinois, namely, are doing a good job with trying to do lots of testing. I think then you can make informed decisions, and you can quarantine, and you can do contact tracing, and these are important things. But on the policy level, I don't think I'm ready to get a quote out.
Thanks.
Philip, this is Martin Corliss from Errol. Very nice talk. Could I get a copy of your slides?
Yeah, for sure. I can give you the full version that this is kind of the Reader's Digest version, but I can.
Yeah, great.
Any other questions?
I had a question for Yiheng. This is Tris. On your, in terms of the attacks, is there so you mentioned that your approaches can catch 99% of the attacks. The 1% that they don't catch, is there some common feature to them, or does that give any insight into how a smart attacker can compromise the system?
Yes. So the 1% that we did not detect is that when so basically still we are actually detecting how abnormal the behavior is. Now, the 1% that we did not detect is their attack trajectories is very similar to the normal driving behavior. So, and we analyzed these cases that that the consequences, those attacks that can bring to the system is also minimal. So in other words, even if we do not detect them, but they can also not make much damage to the system.
I see. Yeah, and then in sort of in control theory, one of the kind of the main
do I
focus.
answer the question?
Yes, that was very helpful. Yeah. So in control theory, one of the focuses has been in recent years on trying to understand these kind of attacks that are difficult to detect, but also can cause damage, right? So essentially, in your case, you'd identified that these attacks that are escaping detection were actually not doing much anyway. So that's great. Is there a sense of whether it's possible to avoid detection and cause damage? So meaning, all the sensors are picking up kind of reasonable things, but then it causes the system to be internally going into some bad state. Do you have a sense of whether that may be possible in the transportation setting? Oh, we might have lost you, Hank.
You scared him away, Shreyas.
I know. Hopefully he joins back. I guess while he's coming back, I had another question for Ran, unless there's other people that had questions. One of the things that struck me was, the Mars mission, there's a sort of, the thing that scares me as a controls designer is these are sort of like one-shot things, right? You invest so much money in a single mission and you send it over there and you've got your controllers designed and everything, and then you're kind of really hoping that it works, right? And any small thing that fails, one of these hundreds of thousands of critical variables fails, and all of a sudden all that work and all that money is down the drain. Is there a difference in perspective in designing for systems like that?
I think design is one aspect. Another aspect is they did do many other tests, and they also send now these days they send a small robot, and probably they want to do the Mars mission in the next 10 years. Instead, they will send the people again back to the moon. So that's their next mission. So what I want to say is they won't do one shot, try just once. They will do it step by step. They will gradually increase their payload and send more people to first the moon's surface, and then send a high payload without humans to the Mars surface. So what I want to say is that they will do more tests before they send the human beings to the Mars surface.
Mm-hmm.
Yeah, still nothing is guaranteed.
Right.
So we did see some failure before and lost some astronauts. So the first time they sent a test robot, it's actually crashed because a sensor didn't get the right number, the altitude number. So the vehicle didn't decelerate at the right timing, so they crashed. So probably they can learn some experience from those tests, and eventually, hopefully they get a high percentage of success rate.
Right. Thanks.
Thank you. I have a question to Laura, I think, and also Jan. So more like how you guys, what do you guys think, and the relation between your research and potential contribution to the COVID-19 challenging situation?
Sure, that's it's an interesting question to ask, but I think it's important to consider how for anyone how your research changes to address large challenges like this. I think that for my research in specific, it's not the sort of thing that can be directly addressing the challenges that arise from COVID, but it is something that can address the secondary challenges. So one in particular that I see is the need for more social distancing and less interaction between people leaves a lot of vulnerable populations who need some sort of assistance physically without the typical assistance they need to get, or wondering whether having that person in their house to help them out is worth it in this situation. And so while we don't want to completely remove therapists and these other people who help out in these situations, creating assistive technology in terms of exoskeletons and other just simple things can help bring a lot of mobility back to people like this when they do have to keep more separate, give them more freedom. So I think that's one area where we can address kind of a secondary challenge of something like this.
Thank you. Thank you. So Ran, what are your
yes. So we actually looking at a special type of robot that will help a large size of humans in a limited room or limited public area to help them maintain the social distance. So with the situation awareness capabilities we can build for general robots, we try to use that to estimate density in a limited room, a limited area, and then use the robot to help people, for example, to guide the human flow in an area to maintain social distance or reduce density of a large crowd. So that's something we think we can contribute.
Thank you. I think Yihan is back. So Shuya,
Yeah.
I think.
Yeah, sorry about that. I don't know why the internet just broke, and I'm using my cell phone now to connect. Yeah, I'm sorry. I don't know whether Sharon has heard my answers, or I can repeat my answers again for his question.
Yeah, that'd be great. Yeah, I think I was just asking whether you think it might be possible to have an attacker that sneakily sends a signal that is not detected but can actually cause damage as well.
Well, yeah, as I said, it's a yes and a no. So the attacker can sneakily attack without being detected, as long as their falsified trajectory or their behaviors are pretty normal. But we analyzed all the 1% cases where the attackers are not detected. But they do not, at least in our case study, they do not cause much damage to the system as well. So on the other words, even they're not detected, it's still fine.
Mm-hmm. Okay, thanks.
Any questions from our audience? And Laura and Ran, Yihan, and Philip. And since we also have some students, like master student, PhD student, and you guys just graduate with outstanding academic performance. If you have like one advice to student research, what kind of advice to their do you have for their PhD study or their master study?
I would suggest talking to people a lot and meet. I mean, it's a little hard right now, but hopefully things will get a little more normal in the next year or two. But getting to know all the professors here in ICON will be a big help. If you convince Shreyas and Xiaoshui to let you meet with speakers like as a group and have like a lunch or something. We used to do that with the control speakers at Illinois, and it was great because we just were able to meet just some of the best people in the controls field from all over the world. You should do that. Building your network is a big thing, especially if you want to go into academia. And I think being at a top university like Purdue with this critical mass of faculty and people visiting is a big advantage that you should definitely take advantage to use.
Okay, so and I will talk about, give one suggestion on the research side. I think it's especially for a PhD student, it's critical to identify those critical problems. What I mean, the critical problem is that if you want to, for example, deploy or implement this system, these are the problems you cannot avoid. So don't spend time or don't focus on those optional problems, but to identify which are the critical problems in the critical path. I think that's very important.
Okay, my suggestion is for PhD students, it's important for me, similar to Yinghang said, find an area they really have interest, because research is a long process and it will last several years. And if people don't really have interest, they may get lost in this long process. The motivation may be the most important thing.
Yeah, I guess I'll build off that a little bit, because I think that it's really important to do something you're passionate about. It's also true to note that you're not always going to love what you're doing, and sometimes you'll be very frustrated with it. But it's definitely important to be excited about the problem you're working on. But I think that in those moments where you are maybe more frustrated, I would recommend, much in the way of network building, build networks with your fellow graduate students, with your fellow master's and PhD students, and take interest in their research. Whether that's through doing small side projects or just through talking to your fellow students. That can be a way to find new avenues for yourself, or just to kind of see other things that are going around in the department around you, which can be very good for broadening your research scope and your research site in general.
One last thing, work and research and building your network are really important, but work-life balance is essential. I don't suggest that everyone have kids during graduate school like I did, but it forced me to have work-life balance. And so, like, whether you have hobbies, like Yiheng shared his hobbies, which I thought was cool, or have some different types of outlet, at least a couple outlets, whether it's physical or a different way of using your brain, is really important. Because, like, I was very busy during graduate school, but the time, and so I spent less time than other people, but the time I spent, I believe, was more effective and had to be. But as a result, like, it was, I wasn't just sitting at my desk hitting my head on it. So I would suggest that you try and find the right balance that works for you, and obviously you have to make your advisor happy, right?
Right, and actually I fully agree with Philip on this. So sometimes you have a very low efficiency, or you're stuck in one problem but you cannot find a solution, makes you frustrated. If you can divert your attention to something else, and when you come back, at least for me, you usually will have a better ideas on this problem.
Speaking about you guys had successfully have a lot of success in your research and also your job application. I believe some of the students also are interested to pursue a career as a faculty. And so what do you think they should spend the most of their energy on during the job application process?
I will give advice that I got, which is, throughout your entire job application process, if you're at that point, don't stop doing your work. You still need to be publishing papers and finishing up things like that, which can be tough when you're at that stage of your research. But you got to remember that, you know, the important part is, you know, showing off the work you're doing. So you want to continue doing that and not kind of take a pause, which is, yeah, tough.
So my suggestion for job application is find the best match. So focus on the jobs that matches best with the applicant's background to improve the success rate. And also, especially for industrial job, maybe make the CV seems to be the best match candidate will also be very important.
I think this is a hard problem, but especially right now, it's going to be probably a little hard in the next year or two. But I would suggest starting early. So like if you're going to apply next fall, like if you're applying right now and you don't have your statements written, you're very, very late. Like I would start writing your research and teaching statement in the spring, like if not early summer at the latest, because you want to get feedback from not just your advisor, but preferably from a couple other people in your network. You want to just be able to rewrite it and throw it out a couple times. And then the next thing is don't get discouraged, right? So like there's only, you apply for a job and there's usually only one position, right? Like max there's like 4 or 5, but that's like very rare. Usually it's 1 to 2, and there's hundreds of people applying for these positions. And so your network plays a big part, your letter writers play a big part. It's just really random, and can be very discouraging because rejection is hard, but like it's just how the game works. And if you want to do it, I mean, you have to try, usually more than once. And by more than once, I mean more than one cycle. So you do like, it takes more.
Yeah, right. I also want to say that don't be discouraged if you are rejected. Many times it's not that you are not good enough. It's because maybe you are not a good fit, or the pandemic starts, right? So it's it's totally not your fault. So for my case, this is my second year cycle of applying, so I get this job. So I think it's natural that, and also don't take it too seriously. Even you get rejected, it's not the end of the world. You are also doing good research or publishing, and someday people will recognize your work.
Do any students have follow-up questions on any of those points?
I have a question. So Phil mentioned that it's harder, it's important to network right now, but it's especially hard because COVID. Given the situation right now, what would you all, I guess those who have experience, suggest to help kind of supplement this lack of in-person networking that's happening because of COVID?
I turned my video on so the new professors could see who I was when I was asking a question. He's my student.
Sorry, hi, I'm Brooks. Nice to meet you.
Yeah, no, that's tough, and I think we're all figuring it out as we go. But I think for me, the thing I've been learning is just reaching out to people, even if it's just over email. I think that everyone kind of knows that this situation is tough and is a lot different. So I think people are a little more, you know, responsive to emails like that, or at least find it more reasonable to just say, oh yeah, let's have a virtual coffee break, something along those lines. Yeah, it's not something that I did during my PhD career, because I definitely benefited a lot from, you know, in-person meetings at conferences and such. But I think that's something that could definitely work at this time, at least.
So my suggestion is to have more communication have more interaction with advisors and other group members. So previously, students and advisors may have more chances to interact with each other, chat with each other at the campus. But now we are all isolated. So like for me, I increase the group meeting from once per week into twice per week. One purpose is just has the usual chat to know what other people's life is, what we are suffering, and give every person a chance to complain. Maybe just complain to others will help. And also encourages the students have some group study time so they can know what each other's situation is, what issues they have. So my main point is increase communication, interaction, opportunities, so we can still feel we are around each other.
Yeah, I think that's great advice. I think having a second weekly meeting is just a vent is an interesting and kind of awesome idea. But I think, yeah, in the same vein, just kind of taking advantage of the opportunities you have and like just using them to the fullest. Like if there are office hours in person, like then you go, and even if you don't have questions about your homework or about the lectures, you just chat and meet the professor. Or if you really if you're too shy to ask a question here, shoot one of us an email, and hopefully we'll have time for like a 10-15 minute call where we could answer questions. I had an idea actually for CDC this year that I was going to like try and make like a hangout group, like a hangout call for me and my friends, and then invite my students and have their students come too. So I think it's going to need some creativity. And so especially because I don't think I want to go to a conference in the next year. Like, I don't really want to get COVID.
Thank you.
Thank you. So almost 12. So Shreyas, do you want to wrap up everything?
Sure. Yeah, I think these are just on that point. You know, ICON is here to be able to facilitate things like this as well. So if there are additional things like, you know, just social events, normally in normal times we would be organizing in-person social events for, you know, all these kinds of things. But for example, if any of the grad students would like to organize anything and would like to have that advertised through ICON, right, this is a community thing, so we're very open to these types of suggestions. One of the things that Xiao Shui and I were talking about from the very beginning was having a graduate student seminar series so that graduate students could present their work, but also, you know, we have this seminar series throughout this year, but as part of that, the goal is to really start integrating internal seminars. So it was so good to see the awesome work that the 4 new faculty are doing. It's incredibly impressive. And, you know, it'd be nice to be able to expand that out to all the other faculty, right? So sometimes we go see what other people are doing at other universities. We don't know what other people are doing at our own university. And so, you know, having more of those kinds of community building events is something that we're very keen to incorporate, and any suggestions would be great. So don't hesitate.
Is there a student emailing list, or is it?
Not yet. So that's something, it's been created, and it just needs to be posted. So that's going to happen.
Great. I was going to ask the same thing. Thank you.
Yeah, definitely. So great. Well, I think that was really great. Thanks so much for, you know, giving us such a nice overview of your work. And I think let me just start my video here. Super awesome. And hopefully that also leads to some collaborations, right? I think just knowing what everybody's working on will be fantastic. And we have many more events coming up, which you'll be informed about. Keep an eye on the website, and we're looking forward to future conversations.
Thank you so much, Reyes. Thanks, Xiao Shui.
Thank you guys, and also thank for all the faculty attending this event.
Really.
Thank you all and all the students. Thank you.
Yes. Thank you, everyone. Bye-bye.
Thanks.